Hey everybody, I need to apologize. I'm sorry I can't be there today. I know I've gone for a meeting on Tuesday, but it's Tuesday night tonight, and yeah, basically I'm really sick in bed, so I'm gonna have to make a video lesson instead. And I guess we'll have to talk again on Monday after your long weekend. So I don't have my my writing pad that's left at the school too, so I'm sorry. You guys just have to make do it the best you can. So. Hopefully this will be a good way though to not lose a day. So what I'd like to do here is on Wednesday, which I guess for you guys is going to be today when you watch this, we'll do topic 4 on oxidation numbers, and then we'll flip that with on Monday when you guys come back from the long weekend. We'll do the lab then. So. Let's talk oxidation numbers. Hopefully this works out well. Like I said, please bear with me. I'm not going to be able to write very nicely because I'm going to use the trackpad on my computer. So you're getting the sick version and the not technological version. So hopefully this works. We've actually already learned oxidation numbers a little bit. I show them to you right when I start the unit. With the idea being that once it actually comes time for us to talk about oxidation numbers, you've kind of already seen this concept. So ideally, if I was here, we would have actually started class with some diploma questions. So I know you don't have these in front of you, but I'm just going to go back in my notes here, and I'll just show you an example of a diploma question that you might be asked. We'll do this one right here. Okay, so the question basically asks what's going to happen to the ore that's here. You got your zinc sulfide, your oxygen gas. It turns into your zinc oxide and sulfur dioxide. And one of the first things I showed you guys is like we can kind of keep track of what's happening by just figuring out charges. So zinc will be a 2+ charge. That's not bad. Sulfur will be a 2- charge. Oxygen is in an elemental form right now, and being an atom, it should have no charge. Then zinc over here needs to be +2 again, so that this oxygen is a -2. This sulfur would have to be a plus charge. Now this one's a little bit tricky. Normally sulfur is a plus, is normally a -2 just based on the column that it's in. But the rules that I'm going to show you on the slides and in our notes in a second here is actually going to dictate that this is going to be a +4. And the reason why it's going to be +4 is that oxygen actually takes priority in this scenario. And oxygen is going to be a -2 charge. And 2 -2 charges for oxygen dictates that sulfur has to be +4. So then as I read through the example here, it says which one occurs. Does zinc gain electrons? And so I'll look here from zinc right here. Does zinc gain electrons? As I look at the charges, no, zinc didn't even change. It's +2 and +2, or 2+, however you're writing it here. So that crosses off A and B because zinc doesn't change whatsoever. And then we're talking about sulfur. So here's sulfur going from -2 to +4. In order to go from -2 to +4, you'd either have to gain protons, but you can't gain protons. So that means you have to lose electrons. So therefore our answer is that sulfur loses electrons, and we know that Leo says Gur, Leo, Leo is oxidized. So, basically what I just showed you then is that's using oxidation numbers. It's a method of keeping track of charges and keeping track of electrons, and coming up with a method to help us figure out who gains and loses electrons. So I'm going to kind of keep this short because I'm really feeling not great right now, and it's midnight. So you guys can read the slide. The oxidation number is the apparent charge assigned to an atom. I think that's kind of a keyword. We're not actually talking the charge necessarily based on our data booklet, like say sulfur. Sulfur normally is a -2, but in this case apparently it needed to be a +4 for it to fit. So oxidation numbers are kind of arbitrary charges I have right here. They're not, like I said, they're not the actual electric charges, but sometimes they're the same. So if it is ionic, if iron is 2+, then yeah, we give it a 2+. Here's a chart you basically just need to memorize. And it's not hard, like you pick this up after a while. First concept basically is that the charge / oxidation number for anything that's an element is 0. Which hopefully makes sense. If I got sodium by itself, like Na solid, if I put a solid right here, there'd be no charge to it. Same thing with chlorine as like the diatomic version of chlorine. It's an element, so it should have no charge. Now if it's an ion, that's a bit different. So Here's a hydrogen in HCl. Now, if you remember from grade 11, HCl is an acid, and acids need to ionize. So we basically found a way to ionize this into H+. And so it's typical that hydrogen has a +1 charge. So normally what I do when I do a question is I'll just go through and I'll find all of the hydrogens all of the hydrogens in an equation, and the hydrogen basically gets a +1, unless it's like, say, H2. If it was H2 in like a gas form, that's back to being an element, and that would be a 0. So here, sorry this takes so long, here hydrogen would have no oxidation number charge. Here it would have a +1 charge, and there is an exception. This is rare. I've never actually seen this on a diploma before. I'm not even sure I've ever tested it before, but it is possible for hydrogen to be a -1 charge. You can actually see that in your data table. -1 is one of the apparent charges. For this to work, the only way that hydrogen can be negative is it needs to try to bond with someone that's very electronegative. And really the only possibilities out there are probably lithium and sodium. I've got an example here of lithium. I don't have a periodic table in front of me, so you guys will have to look this up in a second. But if you guys find the electronegativity number for lithium, I'm going to guess that it's 1.0 or 0.9 or something pretty low. I know hydrogen's number is 2.2. That one I memorized. So the only way that hydrogen is going to be a negative charge is if it somehow bonds to somebody who wants the electrons even less than it does. Normally hydrogen doesn't overly want electrons. Normally hydrogen gives away its electron. But if it's lithium or sodium, yeah, those are pretty much the only two I can really think of that are common. NaH or LiH, which is lithium hydride and sodium hydride. Anyways, long story short, I'm rambling here. It's a -1 charge is a rare possibility. Okay. Going further down the table, oxygen is typically a -2 charge. That's kind of like a set in stone sort of thing, where oxygen seems to always get a -2. But again, there's actually a weird exception. In hydrogen peroxide, this is the only exception I've ever seen. It has to be -1, because if hydrogen is defined as +1, it's a +1. If oxygen has to be a -1, then to balance it, it's really the only way it'll work. Otherwise, basically the concept here is that if it's an ion, then use the charge on the ion. So this may seem kind of purposeless, maybe seem kind of silly, but really the whole goal behind this, if you're asking, okay, Chris, why are we doing this, is that once in a while it may be useful to try to arbitrarily use these oxidation numbers, see how they change, and if the oxidation numbers go up or down, that can help us figure out who gets oxidized or reduced. So I'm going to try to fast forward here a little bit to some examples so I can call it a night. And so yeah, see if you can find this slide. Like I said, I'm sorry. We'll redo this on Monday again. I'm just trying to find a way to make it be a productive Wednesday for you guys without it being completely a lost week almost. So let's do oxidation numbers here. So the logic in HCl would basically be that hydrogen then is +1. And chlorine then would be -1. It's kind of the only way it's going to fit. Honestly, that makes sense. The charge on chlorine is normally -1. So, here's an ionic compound. So this means that magnesium is probably +2 because that's normally its charge. And bromine, if there's 2 of them, better be a -1 charge. So, okay. This next one here is one that requires a little bit more finesse to solve. Basically, the concept is you're going to need a -2 for oxygen, because oxygen is set at -2. And you're going to need +1 for hydrogen. Sorry. So what's going to end up happening here is that in order to make this fit, sulfur needs to be +6. You kind of have to reverse engineer and work backwards. The idea being that, like, how can I say this easily here? We know oxygen, we know hydrogen. Those ones are kind of set in stone. So once I found out those ones, working backwards, the only way to make this molecule neutral is for sulfur to be +6, because then 2 +1s for hydrogen and 6 more plus for sulfur would give you 8, and that would get counterbalanced by the -8 for oxygen. Okay, let me skip ahead just to a couple of other random examples here. Here's sodium hydride. This would be one of the few examples where sodium is going to be +1 and hydrogen's -1. And I'm so sorry, this is not going to be the most effective lesson I teach, but I gotta skip ahead here. So let's just find another example to look at here. Let's look at some oxidation numbers here. Here, the oxidation number goes from 0 to +2. I'm just not going to write it out, so sorry, you just have to listen here. 0 plus 2 means that someone is gaining... No, 0 plus 2 means you're losing electrons. Because if you're going more positive, it means you have to be losing electrons. So this means that zinc is losing electrons. So imagine I wrote LEO there, zinc is losing electrons, therefore zinc is oxidized. That's what this tells you. You could use this one right here then and say, well, hydrogen went from +1 to a form of 0. How do you get from +1 to 0? Well, that means you'd have to gain electrons, so that means that hydrogen is reduced. The reason why this is important is that maybe it's not obvious in a question who's being oxidized and reduced. So if I can skip down, I'm going to find this combustion one at the very end. This combustion one involving methane is a redox reaction. It doesn't appear like it should be, but I assure you it is. And we'll be able to see this in the course of doing oxidation numbers. Just give me 1 second, I need to take a drink here. Okay, so in order to figure this one out, start with what we know are the givens. I'm going to start with this oxygen. It's an elemental form. So an elemental form of oxygen should have no charge because it's an atom. Over here, oxygen should be -2. And hydrogen should be +1. Those are just kind of the things that are always a rule. Those are just such typical charges. It's a good way of keeping track of where electrons are. That means that over here you need oxygen to be -2. And same thing over here, you need hydrogen to be +1. When I take stock of this water molecule sitting on the far side here, then it's balanced because you got 2 +1s and a -2, so that fits. But now I need to reverse engineer and figure out what sort of charges carbon has. And because these molecules here are covalent, it may be kind of, I don't know, you got to work backwards. Don't necessarily look at what the charge is on the periodic table in the covalent bond, just figure out what's logical based on reverse engineering it. So here you've got carbon, it's going to need to be a +4. And I hope that's intuitive. Working backwards, if you have a +4, then this -2 times 2 is -4, then it'll balance out and make a neutral molecule. Whereas right here, this carbon will have to be a -4. It's supposed to be a 4. The idea being that -4 will be counterbalanced by 4 plus 1 being +4. So here, then when we're trying to figure out what's oxidized and reduced, sometimes an entire compound is, sometimes it's just one element in the compound. If I were to ask you who is losing electrons, the answer is carbon is losing electrons. Because this carbon atom right here is going from -4 to +4, thereby losing a lot of electrons. So this is a bit of a change. If I asked you who then was oxidized, loss of electrons is oxidized. And carbon is going from -4 to +4, that's losing electrons. So rather than saying that CH4 is being oxidized, you might actually just say that carbon's being oxidized. If I ask you who's being reduced, this actually occurs in 2 different places. This oxygen right here moves to this oxygen here and this oxygen here. So that means that you're going from 0 to -2. 0 to -2 means you must be gaining electrons. And so by gaining electrons, it means you're being reduced. So that means your oxygen is being reduced. So a typical question might be what element is being reduced? You'd say oxygen. And what element is being oxidized? And you'd say carbon. The hydrogen is actually not something that changes numbers. Hydrogen seems to be +1 the whole way through. So I hope that makes sense. That's basically my lesson. Like I said, I'm so sorry, guys, that I'm not there today. I feel bad for abandoning you for 2 straight days and then having a long weekend, but I hope you'll understand. On Monday, we'll do a lab, and I'll talk about oxidation numbers. So I just need you guys to persevere. Please just try to find something to be productive with for the day. So my best bets are, I hope that you're not too lost on what we were working on. on Monday and Tuesday, just the idea of predicting redox reactions. Hopefully you can do a little bit in the assignment. You can start looking into that. And I'm so sorry. Brain's not functioning at midnight. It's assignment, lab. You probably can start looking at the lab that we'll do on Monday, and start looking at the post-lab questions if possible. And then next week, I guess, will be a pretty busy week because I'll have to kind of do a little bit of catch-up since I was gone this week. So I hope you guys can have a productive day. Have a great long weekend. I hope you guys don't get sick like I am right now. So we'll see you some other time.